So in the first two paths, we talk about the voltage source, current source, and have some example about the node analysis and mesh analysis, and even some example about the super node, super mesh. So if you can fully handle the above mentioned method known as the node analysis and mesh analysis, those and I think you can solve all the resistive circuit without any doubt. And in this path, I will introduce some more advanced technique, a little bit more advanced technique, so that if you can use this, if you can feel comfortable to use the node analysis and mesh analysis, you can sufficiently handle those two methods, then you can move forward. These techniques can help you to make your calculation even more easier. But if you feel node analysis, mesh analysis is too difficult, then just try to get more familiar with the previous method first. So in this path, first I will introduce something called the source transformation. So actually there are two types of equivalent circuit. One is called the definite equivalent circuit. It will simply look like this: a voltage source Vs series with a resistor R. So it's so simple like this. And then other one is called the Norton equivalent circuit. Equivalent circuit. It will be something like a current source parallel with a resistor. The resistive value is actually the same. Both of them are R. Oops. Both of them are R. And we call this node A, B, this node A, B, something like this. Okay, so they are equivalent under the condition that Vs equals Is times R. So no matter if the current is originally look like this, Vs series with a resistor R, or actually you can put R here when they are in series. The order is not so important. So if you can actually replace this part by this one, a current source parallel with a resistor. Or if you have a circuit look like this, you can replace this Norton equivalent circuit by the definite equivalent circuit. They are actually the same with this condition. What does it mean by equivalent? The simple answer is that if I put this circuit in a black box, or if I put this circuit in a black box, if I put the circuit in a black box and you only see the terminal A and B. You are not able to open this black box. And it may be this circuit or that circuit, but you don't really know. And the only thing you can do is you can put different value of resistor here. Maybe we can call it RL. And you can measure the current going in or going out, and also the voltage across this RL. Then you may find that you cannot distinguish whether the black box is this one or that one. Then it is called the equivalent, which means that they look like the same. They have actually the same VI characteristic, that we will call it equivalent. So why it will look like this? So we can draw it like this. We have VS, we have R. In this case, we have IS, we have R in parallel. Okay, so we can write the we can actually solve this circuit as if we know what is inside. So so actually we can only know V here. And also we can only know the I going through. We cannot enter the black box to see what it is inside. So we can only measure V and I for both cases. So actually, for the left hand side, V is nothing but Vs RL R plus RL, and the I is actually Vs over R plus RL. Vs R plus RL, or you should find I first, and then the voltage across RL should be this I multiplied by RL, so that you will find it Vs times RL over R plus RL, something like this. We can solve R, V and I in the for the left case, and for the right hand side cases, so actually we know that this is V, so and actually V also across this R, so IS should be V over IS is this current, okay? So this current will be V, because this is V, so this is also V. Because this node and this node are actually the same, this node and this node are actually the same. So this is V, so the current going through R should be V over R. And the current going through RL should be V over RL. And actually I is equal to V over RL. Okay, so for this case, we factor out V, so it would be RL, R plus RL. And then we will know that V is actually IS times RL plus RL. We only move this term to the left hand side and swap the left and right. And don't forget that we already assume Vs is Is times R. So Is times R is actually Vs. It's actually Vs. So we have RL, R plus RL. So this one and this one is actually the same. Also, I equals to V over RL, which is Vs times RL, R plus RL times 1 over RL. So RL and RL is cancelled, so we have a Vs R plus RL. So actually this one is also the same as this one. So no matter what RL is, you will always measure the same V for both cases, the same I for both cases. So in this case, you cannot distinguish whether the circuit inside is the definite equivalent circuit or the Norton equivalent circuit, which means that they are actually equivalent to each other. So after knowing this, what we can do with it, let me see. Okay. Sample 4.6. Yeah. Okay, so we have the source transformation. So this is the first technique. So let's, ouch. So the example, 4 ohm, 3A, 2 ohm, 8 ohm, 3 ohm. 12 volts. Yeah, something like this. So this question asks you to find VO. What is VO? VO is the voltage across the 8 ohm resistor. So this is VO. Okay, so we can actually use the source transformation for this one to really solve it. So first of all, we can actually see that, suppose this one is A, this one is B. So this part, we can see that maybe we can put the 12 volt here, so that, yeah. Okay, so when you consider this part, this is a definite equivalent circuit. So we can convert it into a Norton equivalent circuit. So this is definite. This is definite. So we can convert it into Norton. So this is 8 ohm and VO. Okay. So when we convert it into 8 ohm, so when we convert it into Norton equivalent circuit, so the resistance remains the same. Okay. Maybe I use the green color. So we have 3 ohm in parallel with a current source. So be careful about the direction of the source. So this should be 12 volt over 3 ohm. 12 volt over 3 ohm, which is 4A. So this is A, this is B. So this is A, this is B, and we connect it to the original point. Okay. So yeah, that's good for that part, and this is actually become the Norton one. And well, we can also change this part. This is Norton. We can convert it into definite. So we just copy the rest of the circuit. 8 ohm, 3 ohm, 4A. Okay, something like this. And this is A, this is B. This is A, this is B. So this one is Norton, and thus the current source is pointing down, so the voltage source is also pointing down. So this is 3A times 4 ohm, which is 12 volt, and then series with 4 ohm resistor, which is actually this one. So A and B, and then we connect them together. So this part becomes the definite equivalent circuit. Okay, so we can see that this 4 ohm and this 2 ohm are in series. So we can just add them together. I can use the red color to highlight it. So we can copy the rest of the circuit. 8 ohm, 3 ohm, 4A. So this is actually 4 plus 2, 6 ohm. So this is just simply series resistor. And we can see that this is the new definite equivalent circuit. So this is definite, This is definite, and we can convert it back to the Norton. Convert it back to Norton. And well, we forgot to, this is actually VO, VO, VO. Don't forget, because you will keep changing the architecture of the topology of the circuit, and don't forget what you need to calculate, because VO is still here. Then maybe after some steps of simplifying the circuit, then the VO may disappear in some of the steps. Then you need to trace back at the end. So when we try to convert this definite back to Norton, so let's copy the other part first. 3 ohm, 4A, something like this, VO. Okay, so next is 6 ohm. This is definite. So for Norton, it is a parallel, a 6 ohm resistor parallel with the current source, and this voltage source is pointing downward, so the current is also pointing downward, and the value should be 12 volt over 6 ohm, which is 2A. So it will look like this. Then we connect them together. So finally, we can further simplifying the circuit. So finally we have this is 2A pointing downward, this is 4A pointing upward. So when we add them together, it becomes 4 minus 2 equals to 2A pointing upward. This 4 is pointing upward, this 2 is pointing downward, so minus 2 here. So we have 2A, and then this 6 ohm resistor, this 3 ohm resistor, So we have parallel resistor. So this is actually 6 parallel 3, which is 6 times 3 over 6 plus 3. So 18 over 9, which is 2 ohm, And don't forget the 8 ohm VO here. Actually, you can regard they are parallel resistor, and then you can further simplify it. But I just keep it due to the VO is the voltage across the 8 ohm resistor. So I just leave it there. And finally we can know that so this current is 2A. And actually this current is VO over 8, and this current should be VO over 2, which is equal to 2. Actually, you use the KCL at this node, so that well, we multiply 8 on both sides, so VO plus 4VO equals to 16. So VO is 16/5, which is 3.2 volt. 3.2 volt. So finally, we get the answer. VO equals to 3.2 volt. 3.2 volt. So 3.2 volt here. Actually, you can trace back to here, then you can know, suppose you know this is 3.2 volt here, you can trace back the original circuit easier, because just for example, you know that 3.2 volt at this node, so you can calculate the current going through here is 3.2/8 is the current going through the 8 ohm resistor, and the current going through this 3 ohm resistor is 12 minus 3.2 all over 3, so that we can also know the current going this way. So as long as we know the current going through this one and this one, then the current going through this 2 ohm resistor is just to add them together. Then you know the current going through this 2 ohm resistor, then you can calculate the node voltage here by 3.2 volt minus the current multiplied 2. And actually you can solve the whole circuit. Okay, so next we consider another example. This one, okay, this one. Okay. So for this one, I will also like to use the source transformation or not. Well, actually, this one we can also use the source transformation to do this. We can use the source transformation to do this example, and also I will demonstrate how to use the linear property to solve this question, because when you need to solve the RLC steady state response, then you suppose you can use the phasor to do the calculation, and if you use the linear property, then the calculation will be easier, much easier, usually. So this is 4 volts, 3 ohm, 4 ohm, 2 ohm. Okay. So supposed to find VO. Okay. So actually we know that this part this part is definite. This part is definite. So for method 1, use the source transformation. So actually, this is the definite equivalent circuit. So we can convert it into the Norton equivalent circuit. So this is 4A and 1 ohm and 3 ohm. This is 4 ohm. This is 2 ohm. And this is VO. Yeah. So next, so these two resistors are in parallel. So 1 parallel 3 should be 1 times 3 over 1 plus 3, which is 0.75 ohm. So we can write it as 4A 0.75 ohm, 4 ohm, 2 ohm, VO, something like this. And then we know that this is Norton, so we convert it back to definite. We can convert it back to definite. So it will be 0.75 ohm, and then the current source is pointing upward. So the voltage source is also upward, and then the voltage source should be 4 times 0.75, which is 3 volt, 4 ohm, 2 ohm, VO, something like this. And then these two are in series, so it will become 4.75 ohm. This is 3 volts. This is VO, 2 ohm. Okay, something like this. So finally, we can simplify VO to be 3 times 2 over 4.75 plus 2. So which is 6 over 6.75, which is 0.89 volts. 0.89 volt. Okay, so this is the source transformation method for solving this question. For method 2, we can use the linear property. Use linearity to solve it. Okay. So what's the point for linearity? Let us quickly redraw the exactly the same circuit again. So this is 4 volts, 1 ohm, 3 ohm, 4 ohm, 2 ohm, yeah, VO, yeah, something like this. So actually, we want to find VO, but actually we need some calculation. But well, the point is there is for this circuit we have one source. So in this case, suppose it is 4 volt. Suppose the source is 4 volt. This is VO. How about if we change this to be 8 volt to 8 volt, then all the current and all the voltage should be double. And if we change this 4 volt to be 2 volt, then all the current, all the voltage should be half of the original case. So now what we want is we try to so we keep the rest part of the circuit to be the same. So we have 4 ohm here, 3 ohm here, and this is Vs, and this is 2 ohm. Now, actually we also want to find VO prime. But if we know Vs when we want to calculate back to the right side, then it may be more difficult. But for this structure, if we already know VO, that it will be easy to calculate from the right hand side to the left side. So how about if we assume VO prime to be 1 volt, in this case this is IO, so IO will be 1/2, which is 0.58. Okay, so in this case V1 will be VO prime plus IO times 4. So VO prime is 1 plus 4 times 0.5. So this is 2, so totally 3 volts for V1. So we know the current IO, so we know the IO here, and we know V1, In this case, we are able to know the current I1 is actually V1 over 3, so it will be 3 volt over 3, which is 1A. And in this case, we know that this current IS should be I1 plus IO, because we apply KCL at this node. IS is going in, IO and I1 is going out. So IS should be I1 plus IO. So I1 is 1, IO is 0.5. So it is 1.5A, 1.5A. So finally, we can get Vs should be V1 plus 1 times Is. 1 is the resistance of this resistor. So 1 times Is plus V1 is Vs. So V1 is 3 volts. V1 is 3 volts. And Is is 1.5. So plus 1 times 1.5, which is 4.5 volts. In this case, Vs is actually 4.5 volts. So let's go back to here. Suppose due to the linear property, all the current or the voltage should be proportional due to the source, which means that here we have 4 volts, so we have 4, and here what we concern is V out, so it is V out. And for the lower circuit, actually all the circuit and the value are the same. So in this case, Vs is 4.5. And for this one, V out prime is assumed to be 1 volt. So we have 1. So finally, we have V out to be 4 over 4.5, which is 0.89 volts, which is actually the same to this one. So if we use the linear property, sometimes the calculation will be easy. For example, like this topology, something like series parallel, and go for several stages. Then as long as we know the voltage or the current of the last circuit element, then we can go back easily, because as long as we know the voltage here, we can calculate the current here, and then as we know the current going here, then we can know the voltage difference, so that we can know the node voltage here, and then we know the node voltage here, we can know the current here, and then we also know the current here, so that we can know the current here through this resistor by adding these two current. And then we know this current, then we can calculate this voltage by this voltage plus the current times this resistor. Then it will be the voltage at this node. And it doesn't really matter whether it keep going for many stages. Then you can still use this method. Then you can just go back stage by stage. Well, finally, I will try to So finally, I'll try to talk about one more method called the superposition, which is superposition. Maybe for this simple circuit, we have 5 ohm. So for resistive circuit, you don't really need the superposition to solve it, but actually, if you can handle this method, then it will be very useful when you need to solve the sinusoidal steady state for RLC circuit, especially with multiple source with different frequency. Then you suppose you really need the superposition method to calculate you really need the superposition method to calculate the multi-frequency sinusoidal steady state for RLC circuit. So circuit look like this, and if we apply superposition method, we first we turn off the free road, which means that part is short circuit, as I've mentioned in the first part of this lecture. So we have 5 ohm. What do we need to calculate? We would like to calculate VO for this circuit. So for this one, 5 ohm, 3 ohm, 9 volts. So 1 ohm, and then the 3 volt is short circuit. 3 volt is short circuit. You can regard it as a 0 volt. So something like this. This is VO. This is VO. So actually, this two is 9 ohm. 9 ohm, and then actually parallel with this 1 ohm. So it will look like 3 ohm, 9 volts. This one is 9 ohm parallel with 1 ohm, which is 1 times 9 over 1 plus 9, which is 0.9 ohm. 0.9 ohm. And actually this one is VO. So VO1 is actually 9 times 0.93 plus 0.9. Something like this. 8.1 over 3.9, which is 8.1 over 3.9. So it is 2 point something. 2 times 2, 7.8. 7.8. A little bit less than 2.1. 2.0 something volt. So for the second step, we turn off the 9 volt. Turn off the 9 volt. So in this case, we have 5 ohm, we have 7 ohm, 3 ohm, and then turn off the 9 ohm, which means this is connected to ground. This is connected to ground, and we have 1 ohm, and then this time the 3 volts should be on, and this is VO. This is VO. So in this case, this is still 9 ohm. This is still 9 ohm. And 9 ohm parallel with 3 ohm, which is something like this. 9 ohm parallel with 3 ohm. And then this is 1 ohm, 3 volt. This is VO2. VO2. Yeah, something like this. And actually, 9 parallel 3, 9 times 3, 27 over 12. 27 over 12. Don't know what it is. So actually, VO2 is 3 times 27 over 12. 27 over 12 plus 1. So it will become 3 times 27 over 39. So it is 27 over 13. So it is also 2.0 something. 2.0 6 7 2.07. Maybe this is also 2.0 something. So actually, so VO is actually VO1 plus VO2, so it will be 2.1 plus 2.07. So it will be, or maybe I should keep the same significant digit. So it will become 2.1. So finally, the answer will be 4.2. 4.2 or maybe 4.1. A bit more. And well, maybe 4.15 should be close to 4.15. Well, so we can use the superposition to solve this circuit. Actually, you can, for this simple circuit, you can actually use the node analysis. You can use the node analysis. You can quickly do this VO over 9 for the left path, and then VO minus 9 over 3 for the middle path, and then for the right path, VO over 1 equals to 0. So we multiply 9 for both sides. VO plus 3VO minus 27 plus 9VO equals 0. And then finally, we have 13 VO. I should still have 3 volt on the. So this one should be minus 3. The original circuit should be this one. So I should still have minus minus 27 here. So finally we have 54 on the right hand side. So actually VO is actually 54/13. So which is 4.1, 4.1 yes, 4.15. 4.15. Okay, so actually we can use the superposition method to solve the resistive circuit with multiple source. It doesn't really matter, multiple voltage source, or maybe one voltage source, one current source. But remember that if it is a current source, when you try to turn it off, it will be open circuit rather than short circuit for a voltage source. This method will be helpful for solving RLC steady state. If you don't really want to use the ODE to solve that. Okay, so that's all for this week, and I'll see you next time.